Okay, so the problem we're looking at today is the USACO 2020 US Open Contest Gold Problem 1 of haircut. So this problem, in order to solve it, you need to know the inversion counting algorithm and the merge sort algorithm. So before you watch this video or attempt this problem, I suggest you learn those two algorithms first. So I will be making videos over merge sort and inversion counting algorithm soon, but after those videos are made, I will be posting the links down in the comments. Okay, so if you have already learned those two algorithms, you should pause the video first and read through the problem yourself. Okay, so you read the problem. So basically, what you're being asked is you have an array of size n, an array A of size n, and n is at most 10 to the fifth power. And now for each j from 0 to n minus 1, you would like to know after all elements in A that are greater than j is reduced down to exactly j, how many inversion pairs are left in this array A. And since n is 1e5, you need to solve it in ON or ON log n or lower complexity. So you can pause the video first and look at and think about this problem yourself. Okay, I assume you thought about the problem. So since this problem is about finding inversions, first of all, I only know one algorithm that can find inversions for an array of this size, which is the algorithm that's developed after slightly modifying the merge sort, which I will demonstrate in a little bit. That algorithm finds the total number of inversions within n log n complexity. So what if we run the algorithm on the original array first, and then for each j, let's just consider how many inversions are removed after each j. And let's take a look at what happens for each j. So first we know the definition of inversion, right? So say the height, those are the heights of the hairs. I know those are like thick hairs, very fat hairs. However, this hair has coordinate before this hair and is also longer than the other hair, so they form an inversion. So does this hair and this hair, this hair and this hair, this hair and this hair and this hair and this hair. So it's a total of 5 inversions in this array of size 5, right? And let's consider for each j, for each pair of inversions, when will it be removed? Well, let's say first of all for this pair, right? For this pair, it will be removed. This pair will no longer exist when j is less than or equal to the second element, the smaller element. Because when j is less than or equal to this element, the greater element will be reduced down to at least the same size as the second element, therefore removing this pair of inversion. And that same applies for every other pair, right? Think about this pair. When j is equal to this smaller element, all the greater ones will be reduced down to exactly the smaller element size, which eliminates essentially this pair of inversion. So now we know for each pair of inversion, it will be eliminated once the j is less than or equal to the smaller one of the pair. So now we just need to calculate for each pair how many inversions exist such that the second element, for each j, how many inversions exist such that the second element is greater than or equal to that j, right? And since we can't directly calculate that, we can, however, calculate the exact number of pairs of inversions with the second element at exactly aj. Not greater than or equal to aj, but exactly aj. Because we know for the inversion algorithm is for every AI that so first of all, this is merge sort. This is merge sort. So you divide the array into the region L to R into two sections, L to mid and mid plus 1 to R. And then essentially, if you know this algorithm for finding inversion, you should know this. You should know how this works. In CNC, AJ is just means how many pairs of inversions has AJ as the second element. And then we take the suffix sum of AJ, as that will be that's SI, and then SI will represent how many pairs of inversions will be removed for when J is equal to I. And then since we already know the total number of inversions minus the number that will be removed for each J is the answer that we'll get. And the time complexity for this algorithm would just be the time complexity of finding the inversions, which will be n log n, the same as merge sort. Okay, so I would say this problem is relatively simple. I saw a lot of other people, like really good people, used more advanced algorithms such as segment tree and tree array. I don't necessarily know if those are necessary because, I mean, it could be easier for them to write than merge sorts but I mean, for me, I suck. I'm in silver, so I say merge sort is the easier algorithm for me instead of segment tree and the tree array. So that's it for this problem, and I hope you enjoyed this video. Thank you for watching.